In this project, we compare state-of-the-art models for both deep learning and boosting, and evaluate their performance in the mineral identification task.
A common method for locating minerals is through remote sensing, which is using aerial imagery usually taken by satellites to make observations about the surface of the Earth. These satellites don't take a normal picture of the surface, but instead separate the different light wavelengths received, which range from visible light to infrared, into several spectral bands. For example, the image on the right is the same area, but with different spectral band combinations, or with only certain light wavelengths. From geological theory, we know that mineral formation is highly correlated with linear features like faults and fractures, and also with the presence of certain hydrothermally altered rocks. Remote sensing allows you to identify both of these, and so it is a very effective and convenient method for locating minerals. Light passing through the Earth's atmosphere when it enters and leaves gets absorbed or scattered by gases and aerosols. This causes images taken by satellites to look hazy and low in contrast. This haziness can be fixed by using one of many atmospheric correction methods, with one of the more common methods being dark object subtraction, where the darkest pixel in each band is located and its value is subtracted from all other pixels in the band. Fortunately, another competition member corrected all the images given and shared them with everyone else.
Convolutional neural networks are a type of neural network where a special operation, called a convolution, is applied to an image to extract information and make predictions. Filters apply these operations, and each of these filters can encode a certain type of information. For example, a set of filters, called a layer of the network, can be trained to detect lines and edges, and the next layer can identify shapes, and the following layer after that can detect complex objects, such as faces. With the potential to learn deep representations of the data, a CNN is a very promising avenue to explore in this challenge.
Our project uses two ways of modeling with CAD Boost. In the first modeling, random holdout, a two-class model is trained on raster pixels inside and the randomly selected set of pixels outside the search distance, so that the model is sensitive to the geophysical character of gold deposits in the area of interest. The model is then applied to each pixel in the 11-band raster in order to generate output raster with values representing the probability that the pixel belongs to mineralized class. We can validate this probability against a set of pixels not used in model training or the holdout set. The second model is called occurrence holdout and resembles the one used earlier, but instead it trains unique models for each occurrence, holding out a single occurrence at a time. The end product is a stack of predictions like the one plotted earlier, which when averaged yields a final perspectivity map. In general, CAD Boost proved to be a decent way of mapping deposits, as it offers quite a variety of metrics. In particular, we used multiple regression as a loss function and accuracy as an evaluation metric, which in fact was quite high, 97%.
The faster dense spectral spatial convolutional network is inspired by Wang et al.'s network, the fast dense spectral spatial convolutional network, which applies a dense neural network structure to the problem of aerial object detection. Our model improves upon their work, fixing errors and adapting the model for Landsat 8 data, which is multispectral in nature. The model architecture can be seen on the slides, with a code for the model and data intake pipeline offered on GitHub. Submitted to the challenge are our predictions by FerdySSC, which have latitude, longitude, and a predicted class from not a deposit / not notable, nickel, manganese, silver, lead, copper, iron, uranium, and gold, and a corresponding probability for that prediction. These predictions span the entire coverage of Landsat 8 images of the Gala region. As an example, here's an area with ground truth labels from the SARIG map on the left. We can see that FerdySSC's predictions follow very closely with the ground truth labels, and it, along with a CAD Boost model, exhibits signs of following the natural geographic features, proving that these models are generalizing to previously unseen data. Future prospects of our pipeline involve incorporating higher dimensional input data, such as hyperspectral images. We can also extend the performance of our CAD Boost model to generate target sites and create a more refined data intake pipeline for that model. We hope that our project reinforced the fact that while FerdySSC performed admirably, currently, with sparse pocketed data, decision tree classifiers perform better in the field compared to deep learning classifiers. With our work on Landsat 8, we hope that we've opened up an avenue for future development in the deep learning field for remote mineral identification. Thank you for listening to our presentation.